we have to draw a force diagram for the skier, and we did that together. If I wanted to recopy some of this, I could do that by moving my forces. I've got one that's directly downward. That's force due to gravity. I've got friction going backwards, and then I've got a normal force that's 90-degree angle to that. So there's my force diagram. We drew on here that our horizontal slope was going to be the line that friction is on, and our vertical slope is going to be where normal force is. We also were given an angle. So we've got a 35-degree angle down here. So if I imagine a horizontal line with my 35-degree angle, I'm trying to just keep all my colors the same, then we can figure out where some of our angles go in the rest of this. So this angle here is going to be, this is a right angle, then that angle is going to be 55 degrees, and we're going to have our 35-degree angle in here. So that's kind of how we can keep track of our triangles through that, so that we know where everything should lie. You guys have any questions about the force diagram for the skier? Again, this is the very end of worksheet number 3. So we finished it, but we didn't actually talk about it. So if I want to determine the skier's weight, remember the weight is going to be equal to the force due to gravity, because weight is different than mass, especially in physics class. So that's going to be mass times acceleration due to gravity. We're told that our skier has a mass of 90 kilograms. So we're going to do 90 kilograms times minus 10 meters per second squared, so that our weight, our force due to gravity for our skier, is going to be minus 900 newtons. So that's what we should have for the answer to part B. Next, it says determine the component of the skier's weight that is supported by the hill. And so what we're looking for here is the component of our force due to gravity that is opposing normal force. So how much does the hill have to push up to hang on to him? To figure that out, I'm going to draw my rectangle here, so that I've got a line that is along that vertical axis that is a component of gravity. So I'm going to write FGY because it's my vertical component. And to figure that out, I'm going to use, let's see, if this angle is a right angle, then FG is my hypotenuse, FGY is my adjacent leg. If that's my adjacent leg, then I need to use cosine. So I would say that the cosine of 35 degrees is equal to my adjacent leg, FGY, divided by whatever my FG is. So to solve for FGY, I have FG times the cosine of 35 degrees. We determined FG was going to be minus 900 newtons times cosine of 35 degrees. So I got minus 737 newtons. Remember, the sign here is just what direction it is. So if you're doing it on your paper and you actually go back up to your force diagram and you write that that is equal to that's equal to 737 newtons, that's okay, because it's telling me what direction it goes by being on the picture, right? You guys have any questions about that part? How are you doing? Getting them right? Okay. For part D, determine the component of the skier's weight that pulls the skier down the slope. So this is going to be the part of the force due to gravity that's opposite of our friction force. So on our force diagram, we're looking for this line, because this is going to be equal and opposite of that. This one would be opposite this one. Equal magnitude, opposite direction. For this guy, we know the angle in between our vector for force due to gravity and our vector for the force pulling the skier down the slope. If this is a right angle, then FG is again our hypotenuse, and we've got an adjacent leg. I'm going to label that guy 2, FGX. So down here, I could say the cosine of 55 degrees, it's different than the one above, is going to be equal to FGX over FG. So FGX is equal to FG times cosine 55. Let me do that one in the calculator. Oops. Minus 516 newtons. Again, I can write that up here too. Any questions about that one? Again, there's more than one way to solve these. So if when you do your triangle, you decide you want to use the cosine of 35 to solve for FGY and the sine of 35 to solve for FGX because you know that this line is the same direction and the same magnitude as that line, that's okay. You can do them both ways. Normally, my answer keys will have both, so it's no biggie to me. And then lastly, what's the total force of friction and air resistance acting on a skier? Explain how you know. Well, what it's asking for is how big is this backwards force up the hill? How much force does our skier have to overcome to be able to slide down the hill? And so if he is moving at a constant velocity, which means there's no acceleration, that's telling us that those forces have to be balanced. And so if they're balanced, that means that this one that's blue here, FGX, has to be equal to the force due to friction and air resistance and all this stuff. And so we can say, because, I'm going to say all of this, because velocity is constant. And have you guys ever seen this symbol before where you have like 3 dots in a triangle? That symbol means therefore. So it actually does save you a considerable amount of time. Because velocity is constant, therefore acceleration is 0. We know that FGX equal to, the magnitude of FGX is equal to the magnitude of friction. So the force due to friction and air resistance must be equal to my FGX, 515 newtons. All right, do you guys have any questions about the skier? You're feeling pretty okay about the skier? Okay, so we're going to start with worksheet number 4, which hopefully you guys took a little bit of a look at the other day. There's a little bit of information up on the top here. This is force diagrams and statics. Have you guys ever seen the word statics before? Maybe. It usually shows up with dynamics. So when we talk about physics, we talk about dynamic forces and static forces. And things that are static are things that are not moving. They're stuff that's just hanging. So no moving, no accelerating, constant velocity. This is a clue that's telling us that forces should probably be balanced. Probably balanced. So this first problem here is a problem about a volcano. At one point, my husband was thinking about being a volcanologist, and then he decided that there wasn't a lot of employment opportunities as a volcanologist. Plus, he might have to actually like touch magma that's on fire, and that seemed like a very substantial hazard. So my husband started as a geology major and then became a chemist because he thought there would be better opportunities for employment that way. But yeah, anyway. Volcanology. So volcanologists need a lava sample from an active lava pool below a plateau inside a volcano. Oh no. Have you guys ever seen people do this, by the way? They usually have like a cast iron ladle that's like 5 feet long, maybe a little bit longer. and they stick it down into the lava and scoop stuff out. It scares the pants off of me, and I'm a geology person. That's probably why I'm in paleontology. But anyway, after one end of a rope is anchored to a rock, this is a physics problem not written by a geologist. I'm not sure that you would use a rope for this, because if the rope touches the lava, what happens? It's on fire, and now you're not going to get your sample, and you lost your bucket. Anyway, so one end of the rope is attached to a rock, and a scientist hikes around the plateau rim so that the rope and a cable hangs over the lava pool. The cable is dipped into the lava pool, and then the lava that congeals on the cable is retrieved. When the cable with the lava sample has a weight of 125 newtons, how large is the tension on the rope? Hint, make your force diagram for the junction of the cable and the rope. And don't worry about the fact that the rope has weight too. So we're not supposed to think about that. All right, so here's our cross section, so that we have an idea what's happening here. So what these guys have decided to do is anchor a rope to one side of a volcano, walk around the cauldron, and now the rope is tied to this person. This seems dangerous, right? Like this is like tug of war that could go really wrong. Usually you play tug of war over a creek or something. We did that my senior year on a retreat. Anyway, so we've also got a lava pool down here. So this is where we're hoping to get the magma from. What they're going to do is this person is going to release some of the rope so that it has some slack to it, so that this cable dips down into the pool. Some lava is going to stick to the cable, and then we're going to try to pull it back up. This is their plan. All right, so the first thing it says, how large is the tension in the rope when we have a weight of 125 newtons on the cable? We're going to need to draw a force diagram. And then we're going to calculate how much tension would be needed if we decrease that angle there to 5 degrees from 38. So first we need to draw a force diagram. All right, so we've got a rope with a junction, right? We've got a cable that hangs straight down, and that cable has a weight of 125 newtons. So far, so good. I'm going to draw a dashed line for horizontal here. And then we've got our rope sticking up in either direction at an angle of 35 degrees. Is it 35? It's 38 degrees, sorry. There's my force diagram. Sorry that got so tiny. Can you guys see that okay? We know it's 38. So first we need to figure out tension in the rope. All right, so in order to do that, I'm going to think about this as a couple of rectangles. I'm going to have a vertical line here that matches the vertical over here. Can you guys see that? I'll zoom in for you. So I've got a vertical line here that matches a vertical line here. And the other side of my rectangle is going to be the pull to the side. And I'm going to need a similar thing on the other side. I've got an up component. My rope is being pulled up. And I also have a horizontal component where I'm being pulled to the side, like that. I've got two forces that are going to be opposing this one, right? So the pink, I've got these as orange and pink. So if I've got tension on one and tension on the other one, do we expect that those are going to be equal? What do you guys think? And if they're equal, what are they equal to? Did I lose you guys? Because if this angle is the same, right, and both sides of the rope are supporting this weight, then what that's telling us is that the upward forces that's part of the tension of the rope, those are going to have to be equal to this downward force. So we could write an equation for this. FT1 plus FT2 equals 125 newtons, right? If that's true, then either of them has to be half that. So what is that, 62 and a half? Yeah. So we know that. All right. So now what we have to do is figure out each of these tensions. Should they be the same? If the angle is the same and the vertical forces are the same, then we would expect the tension in each of those ropes to be the same, right? So that means we only need to solve once, which is really nice. If I want to use this lower triangle here, and I say that this angle in this corner is a right angle, then my FT2 or my FT1, we'll do it over here because it's FT1. Then our FT1 is going to be our hypotenuse. Ooh, this one, I named them the same. Shouldn't do that. I'm going to call these FT1X, FT2X. This is the vertical part. All right, so if I'm going to solve for FT1, I'm going to use this relationship here with the opposite side, the orange line, the opposite side, and the angle. So if I'm using the opposite side, that's going to be my sine. So we can say the sine of 38 degrees is equal to FT1x, right, the orange one, divided by FT1. What I'm trying to solve for is, is this. Worst circle ever. And we know that this guy is my 62.5 newtons. So FT1 equals 62.5 divided by sine 38. We're expecting a number to be larger than 62. I got 101.5 newtons. What questions do you guys have? Does it make sense? Did anybody get there on Friday? It's a little bit tricky, isn't it? So for part B, the second part, it says how much tension would be needed in the rope if we decrease the angle to 5 degrees. So we're going to do the same thing, but we're going to change our angle. And so instead, we're going to have a very steep rope, right? But this side is still going to be 62.5. Only now this angle in here is going to be 5 degrees. So the question then is how much tension do we need in that rope to be able to do that? So keep in mind, this is going to be about as much force as trying to hold up something that weighs 10 kilograms. You might be able to hold up 10 kilograms, right? It's like a bag of dog food. That would be okay. If we change it to 5 degrees to figure out the tension in the rope, it's going to be 62.5 newtons divided by the sine of 5 degrees. And that value, do you think you guys would be able to do it if it was almost straight across the lava pool? I got 717 newtons. It's like trying to hold up something that's 70 kilograms. It's a lot heavier, right? 7 times as much force on each rope. So what happens if one person can't hold on enough? We end up losing our sample, right? It's not that big a deal. Hopefully, if these guys are collecting lava samples, they understand that instead of falling into the crater, they should just let go of the rope. It's not worth fighting about. You guys have any other questions about this one? No questions? Okay. So I'm going to help you guys set up the guy with the box here. All right, so a man pulls a 50 kilogram box at a constant speed. That's important because that means our acceleration is 0 meters per second squared, which tells us forces are balanced. He applies 200 Newton force at an angle of 30 degrees. Draw a force diagram for the box. So my box is going to be experiencing gravity. I can look at this and I can say, okay, 50 kilograms times minus 10 meters per second squared means that this downward force is going to be minus 500 newtons. We are told that we've got a force here where a box is being pulled with, these are not to scale, 200 newtons of force at an angle of 30 degrees. So that's what our force diagram is going to look at. So what you guys need to do with this is write an equation, calculate normal force on the box. Remember, normal force is going to be the opposite direction, right? Write an equation for all the forces and components on the box in the horizontal direction. Calculate the size of the frictional force. Okay, I'm going to tell you guys something about normal force here. Normal force is there to think about it a different way. If you're pulling up on an object, that may take away from your normal force. So what you'll find here is that some of this force is being supported by this 200 Newton upward pull. So you're going to need to figure out what that component is over here. So find that component first, so the force of the pull in the y direction, and then solve for normal force. Another way to think about it is that if we write the vertical equation for this, we're going to have F, the force of the pull in the vertical direction plus normal force equals gravity. Okay, so this is going to be smaller than gravity because of that. So if we pull upwards on something, the surface it's sitting on doesn't have to push up as hard anymore. If it did, that object would fly up in the air. But we know that it doesn't because constant speed and it's sitting on the floor. All right, so I'm going to let you guys work on that for a little bit. If you have questions, please let me know. I think you guys should be able to get through that problem today and maybe try the next page too. All right.